little bit before where we ended just to make the whole thing continuous. But before that, a couple of things. So I have the homeworks from last time. Homework 1 has been graded. So there were 4 problems, right? But remember there was a discussion in the class about the 4th problem, but about to be redone in a different way for the next homework. So I have not graded the 4th problem, and I think this has been to everybody's advantage because a lot of people had not done or like kind of died in the middle of the 4th problem. So anyway, this is here. It's out of 30, 10 each for each. And I have usually, I mean, if you have finished it close to the close answer, you have got full points. If you have finished half of it, you have got half points. So that's roughly the rubric. This next homework is due today, right? So 2 of you have already given it here. Before class or after class, well, not in the middle, I guess, but please put your homework here. And what else? Somebody had said they want more time. I don't know if everybody wants to have another day or 2, it's okay. Thursday, don't take any more time than Thursday. Otherwise, I'll have to ask somebody to authenticate it. I cannot give you too much time. Okay, so now let's start. So let me remind you, we had the following expression from last time. Am I writing it big enough, I guess? Yeah. Is it clear in there? So this was the vacuum persistence amplitude in the presence of a source. So the idea was you start with the real vacuum of the theory and you switch on some source, which would mean some detector or some experimental gadget which shoots out the particles corresponding to this operator right now, because I have a hat there, and then you detect it and then you switch it off eventually. But you calculate this in the presence of J. This was this quantity, and then maybe we did show, or I will show, that you can calculate all the correlation functions from this quantity. So this was the somehow, you know, the block from which you could get all the interesting quantities that you wanted to calculate. So a couple of things. So this is the vacuum state of the full theory right now. Phi is an operator as of now, because even though we did start path integrals, and at the level of path integrals it will become a number, or a C number, or a bunch of C numbers for every x. But before that, because we are coming from the path of canonical quantization, it's an operator. And it's a Heisenberg operator. Right? And so this depends on time and so on. And yeah. So, and the way to get the endpoint function, for example, was to expand in J. So that was the J perturbation theory. So there is a distinction between there are 2 kinds of perturbation theories. One is the J perturbation theory. Every order by order in J gives you that endpoint function. If you go to 2 orders in J, it gives you 2-point function. If you go to 5 orders in J, it gives you 5-point function. But that would be the 5-point function of the field phi in the true vacuum. That answer would be to all orders in the perturbation lambda, where lambda is, let's say, the generic small number in front of the interactions. Remember, so for the interaction for the Hamiltonian or for the Lagrangian, we split the Hamiltonian or the Lagrangian into a free part and an interaction part. And we said we will work in the limit that the interaction is small. So that will be another perturbation on top of this J perturbation. Okay, so the J perturbations will give you different endpoint functions, and each of them will be another series in the lambda perturbation. Then we showed last time, this is still review, so then we showed that this quantity is equal to, this is the epsilon from the I epsilon, and then there was a path integral involved. So at this point, phi has been demoted to just a C number, no operator or any fancy stuff, right? And you might have seen this from earlier class that this, in canonical quantization, at least when you go to the Feynman language and so on, this factor is actually, well, this denominator is actually factoring out all the bubble diagrams, all the disconnected diagrams that happen for every process, which they are anyway infinite, and this just drops it out. Notice that this is just the numerator with j equal to 0, right? So this is kind of like a normalization. Now this epsilon, so this is again going back to the things that we had done last time. This epsilon had shown up last time in the quantum mechanical version of the path integral. In the following way. We had an expression like this. So this is minus IH. And let's say I work in infinitesimal time, dt. And then there was a 1 minus I epsilon. Okay? Because the t becomes t times 1 minus I epsilon. Okay? The way to, at least in my way of understanding that is, how do you get the sign? Well, first of all, it will give you the right answer. It will give you something which will converge, so that's good. But how do you know? The thing is, the Hamiltonian corresponds to time translations. So the factor there in front of the Hamiltonian also corresponds to energy or mass. And you can look at the 1 over p squared minus m squared plus I epsilon. And you can see that m squared goes to m squared minus I epsilon. Right? This is how it's supposed to look like. And so this, if you can just bear with making m a little complex, and then you would say, okay, this is how m should be tracked, this is how energy should be tracked, and this is how time should be tracked, and you know from the earlier discussions that if this was a minus, it would be bad, right? So anyway, so if you do that, so what do you get? It will be proportional to, and there will be a plane wave factor here, right? E to the IPX dot, I guess. So this would be coming from a PX, the overlap of a P state and an X state. I think this expression, I will not go into the detail here. I think this expression was derived last time or something similar to that. Is that true? Yeah.
So I understand what you're saying. I'm just curious. What is our overall goal right now?
Well, the overall goal right now is to, first of all, start the process of path integrals for fields. So because we did a lot about quantum mechanics. So things that you have seen in quantum mechanical version we'll do for the field case. And then from that we'll build on slowly to free field theory, scalars, then complex scalars, and then fermions, because fermions are inherently complex. And then Grassmannian numbers will be just thrown to you. You cannot do anything else. It's not to make sense of the whole thing. So this is the rough plan. Okay.
Is the fact that phi here is the Heisenberg operator why the Hamiltonian isn't in the integral? We've just done some multiplication on either side.
Here.
Yeah.
Well, this is the definition. So this is saying go from this vacuum to that same vacuum in the presence of source. So you start with vacuum, you switch on the source, and you go to vacuum.
Mm-hmm.
So this does not have the Hamiltonian. I mean, even if you did have something here, Hamiltonian acting on the ground state of the true Hamiltonian acting on the ground sets of the true Hamiltonian will just go to the true Hamiltonian. It will not do anything there, right? It's like the Heisenberg of the H Hamiltonian acting on 0 will give you 0 energy, so it will not do any phase changes or anything. Okay, review this. It should be straightforward.
Right. But before we had in this time-ordered exponential, we had the Heisenberg operator.
Oh no, that was a different thing.
Sorry, we had the Hamiltonian, and then
that was a different
the one
thing.
acting on the ground state gives 0, but there's this infinite product of Hamiltonians with the sources. The source can take
So
it
I
out
don't
of the
think
vacuum and then.
I don't think that was calculating this quantity. When you calculate this quantity, then you have to integrate over all the. So you might have something like this in mind, I guess. In the quantum mechanical version, there is an xi to xf, right?
Mm-hmm.
But you see, xf is you then integrate over xi and xf to get this. And so the formula as written is correct.
I think what is being said over there is that that is the vacuum with J put in, and these omegas over there are the ones with J equals to 0, right?
Oh, these ones?
Yeah, these ones are with J equals to 0.
Well, so this is, I mean, this is a symbol. Right? I mean, this just means that the true vacuum, then you switch on the J,
Yeah.
and you calculate this quantity, whatever that is,
Yeah.
and then you will eventually, so I mean, this is still not a physical thing as of now, right? You to calculate the endpoint functions, you will have to differentiate and set J equal to 0, so that is correct. In the end, you will set equal to 0. But how is that related to the Hamiltonian thing? I am not sure. Where is the Hamiltonian coming in there?
I think I might have mistaken notes from an earlier lecture, so I had a misunderstanding.
Okay, well, yeah, I think there is a Hamiltonian in the time ordered, but it's not this quantity. I think it's a different quantity. So you can do this integration, and this gives you so I did it because I have it in my notes, but you can say this is a Gaussian integration in P with a P square coefficient. Don't worry about the convergence factor will come out just because this epsilon minus I epsilon times minus I is minus 1. So there is an overall damping factor in front, and this is making the Gaussian integral well behave. And this actually, I can write it like this, or I can write it. Okay, it's the same thing. And then anyway, so the point is, this scales as e to the minus epsilon. If you take this and this, m over 2 x dot squared. So recall, this is the energy of the free particle. Right? So it's a positive quantity, and epsilon is positive. Epsilon goes to 0 from above 0. So this is a well converged quantity. Okay? So this is how we are regulating the path integral in some sense. The same thing will happen for the. So when we go from this quantum mechanical path integral version to our field path integral version, so in quantum field theory. By the way, is this visible? Yeah, I guess so. Yeah. In quantum field theory, we have the following expression: right? E to the is plus j phi, and this will go as e to the minus epsilon, and we'll come back to this. Okay, so integral phi dot square plus grad phi square plus v phi minus j phi. Okay, something like that will happen. So we'll come back to that, and we'll derive something close. But to get your intuition correct, you are. Trick like this will happen, and effectively, remember there is a minus v of phi usually in the Lagrangian, but it will change sign, and you will get energy there. Okay, and I think this is related to somebody had asked a question about the Euclidean version of the path integral in one of the homework problems. You look at it; it's not kinetic energy minus potential energy; it's kinetic energy plus potential energy, and so that happens because of it's a similar. But anyway, the point is this is a positive definite quantity. Squared potential is always, it's the minimum value of a potential is 0, or it's always bounded by in that sense. And so it's e to the minus epsilon times a positive quantity, so it's again well converged. Okay, so now let's do something else. Yeah, so again, this is just to clarify this symbol d of phi. What does it mean, right? Because in practice, you might want to calculate it, which probably you will not do, but still, it's the formal notation for something. You should know what it stands for. So remember, phi is a field, it's a C number. So this is a shorthand for this. This is a product. phi at some given space-time point. That's one variable, and you integrate over that variable. And then, so this is like an infinite number of integration variables. Okay? And usually the way you do it in practice, maybe on lattice or maybe sometimes in computer simulations, lattice is one example. Or even in your head sometimes to understand it conceptually is you discretize it, you replace this by this. Now we will go over it, but you see, this already does something nice. When you discretize from here to here, you are effectively saying that that space-time x is not continuous anymore, it's discrete. So that already puts some kind of a cutoff in your theory, which is what you need to do anyway when you do perturbation theory, because things start blowing up and then you have to do a polyvelars or an epsilon, 4 minus epsilon dimensional regularization. So this is another regularization which you do anyway, and this does that. Okay. So, yeah, so this is what I was saying. So there are two perturbations, J and lambda expansion, and lambda perturbations were UV sensitive, or loosely say divergent, and that was already taken off. So taken care of by by d phi I mean phi and xi, obvious notation. So this discretization already does that now, but so that's one regulator, or which is taking care of one UV sensitivity. The other regulator is this epsilon regulator. So there are two things which are regulating. So this is one thing, and this is the second thing, right? We saw it right now. Epsilon is making sure that the path integrals are converging in some sense, because you're not allowed to do path integrals or the Gaussian integrals. You're doing free field theory right now, right? This is the free Hamiltonian for quantum mechanical working. So it was not strictly correct that the answers would make sense unless you have something which converges. And so the epsilon was doing that trick. It was doing a completely different trick in the canonical formalization. Remember, the I epsilon, the plus I epsilon was gotten by getting the time ordered 2-point function, or choosing the contour in the complex plane when you do the time component of the 4 momentum p, choosing the right poles and so on. So it was a different thing there. But anyway, they are, of course, the same epsilon. So this is doing the trick. And again, let me remind you, this epsilon, we understood this, and hopefully you remember from discussions of last class or before that, this epsilon was coming in the path integrals by letting t go to t times 1 minus I epsilon, I just say. It's m, h, energy, t, they all come together. And this was also doing this thing called projecting on the vacuum. So when you, maybe this is how it's related to your question. I think the Hamiltonian acting on the vacuum with a time made slightly imaginary picks up only the ground state, and because everything else goes to 0 as epsilon goes to 0. Unless the energy is 0, where the epsilon does not matter. So I think this was discussed in the last class. You guys remember that? Or yeah. Okay, so that's where the epsilon is coming from, really, in the path integral. Okay, that's how we could say that this time is that. So it's actually also projecting the vacuum. Okay. So all this good. Now let's go to actual path integrals. Let's see how to calculate things. And we'll start, of course, with the simplest thing that we can start with. Free field theory, scalar, real scalar.
The first formula you have up there, it just seems to me like it should be d phi I of x.
This?
Yeah, d phi
Well,
I.
phi of xi is phi of I.
Yeah.
So it's the same thing. There does not have to be another subscript here, because think of it right. I mean, you don't say when you say phi of x, you're say, okay, phi of 1 is something, phi of 2 is something, phi of 5 is something. So
I thought the point was we were changing the function phi was changing. We were doing like the path integral over all the functions.
But that's why I am integrating over all such phi. Like this is equal to d phi at x1, d phi at x2.
No, what probably he's saying is that
I don't think there should be a subscript on phi.
So those phi's are d phi of x1 is not the same phi as d phi of x2.
No, it's not.
Right. So you're using the same symbol for that function, even though the functions aren't the same.
D phi of x1, but they are independent variables, so this is what it means. There will be two integrations.
the integration variable, not the x?
See, it's d phi. So actually, yeah, maybe I think in a technical sense you are correct because there is no x here in that sense. So which I did here anyway, right? This is your integration variable. This whole thing is your integration variable. And there are a lot of them. Okay, one for each x. Now I could call that as my phi 1, phi 2, phi 3. I could say it's phi at x1, phi at x2, phi at x3. No. At that point, x is just an index, because you have discretized space-time. Okay. Fair enough? Yeah, but this thing is, the first time you see, you always get a little unsure, is it this or this, and then it does make sense. So we'll get to perturbation theory, but let's do first free theory. That is this lambda, which is the generic coefficient in front of the interaction, set that to 0. And also, forget epsilon for now. The whole epsilon story that I told you, hold it for now. We'll track it, we'll see what it does. But so the thing that you want to calculate is this. So it's a scalar in the presence of a source, and it's a real scalar, so the kinetic term, then the normalized kinetic term has a half there and so on. Okay, well, you know this. But this is just the action, the source party is the action. And then I have put a source there. The integration is for the whole, because these are also functions of x, so this has to be integrated over, the whole thing has to be integrated over. Okay. Now, so how do we do this? And this will actually clarify the question that you were asking. Now, what does this d phi mean? Okay. So to calculate this, and now we know that Gaussian integration should be doable, and this looks like a Gaussian integration. There is two phi's, whatever that means, right? It's an integration over phi, right? So how do I proceed? And at this point, since we will show this calculation, it will be clear, what does it mean actually. So before that, let's do this. So we will come back to this expression, but let's evaluate this by considering something else. So consider this. Consider bad notation. This I and this I are not the same thing. Xi. Okay, so this is, Now, this dx vector means that it's dx1, dx2, dx3. Okay, so this is a shorthand notation for writing a lot of integrals. Okay, so this effectively means dx1, dx2, from 1 to till this sum goes to. Okay, this might go from 1 to n. And you see this factor, it is a Gaussian integration as written. It's just in more than one variables. Okay, it's an n-dimensional Gaussian integration. To do this, so let's forget for a minute that there is an index I and j. Let's just do the simple case. So what will you get? You will get e to the, so there will be some constant, so this will be constant. call does not depend on j. The constant usually is given by pi over square root pi over the square term. Okay, so it usually does not have this j there. And that's good because we eventually want to differentiate with respect to j and so on. Okay, we will get to that. And so if something is independent of j, you don't care. Okay? You just factor out. When you divide, when you normalize it, it correctly will go away. So it will be constant times e to the, so it will be j squared over 4I. And let's say this is just a number for now. Okay, so there's no index, just one-dimensional integration. So this is the formula. Let's see if this is correct.
So for the matrix, would that be like the determinant?
Yeah, so that's what I was going to say, yeah. So this will become, or e to the minus I over 2, j, 1 over delta, j. I think there is a 4 or something, supposed to be here. Oh, I am considering this. Okay, this is just to make it parallel to the half here. So anyway, this is what it looks like. Now let's make it more complicated. Now let's say if I have 2 of these, or maybe 3 of these, or 4 of these, okay? So more than one integration. What do you do now? As correctly pointed out, this just will become a delta inverse there. The determinant will come a little bit later. I think the determinant shows up in this constant here. This constant, I think, goes as pi over delta, square root. And if there are more than one delta, in other words, if there is an index over delta, then this will become determinant of this matrix delta ij. But it does not contain j, so it's okay. It's not important immediately. Now here what is happening? So to understand this formula, or to at least get some intuitive sense of how to generalize this, think of it as the following. Let's say that these xi's are such, I mean, you can think of this as a matrix equation, right? X transpose delta x. Think of this, so think of x as such that it's an eigenvalue problem. In other words, delta ij times xj is lambda xi. Okay, so let me write it here. For the case with indices. For the case with indices, consider delta ij xj equal to lambda xi, and also a lambda I xi, but this I is not summed over. Okay, so this is a matrix equation, delta ij xj. So it's delta dot x. This should be equal to something. I think this should not be right. Yeah, lambda times x. So this is the matrix equation, and this is what I will use there. And let's say if I have two x's, then there will be a lambda 1 and a lambda 2. So for each x, there is a different value. If you do that, notice something very interesting happens. When you have, let's say this acting on, so let's say I and j go from 1 to 2. Okay, so there are two x's in that sense. This will become lambda 1 x1 and lambda 2 x2. So you will simply be getting x1 squared and an x2 squared. And it's in the exponential, so it will just factor out. Right? Similarly, this sum, x1 j1 and x2 j2 will just factor out into 2. So it will just become a product of two Gaussian integrations. Okay? And of course, there is nothing special about 2. This is true for 3, 4, 5, whatever I want. And so you can already see this expression will simply become, so in this case, I should write it here. So in this case, the final answer will be, I will get a constant. I will write the expression there again. So if you don't, e to the minus I over 2 ji. So there will be more than one terms for each integration, right? Because this whole integration is a product of, let's say, 5 integrations. So for each of them, I will get an answer. I can combine it again in the exponent, right? Because it's a bunch of exponentials. Ji 1 over lambda I ji, or 1 over lambda ji. Okay, so J1, so let me say this in a correct way. I do need an index here, but not the same index as this. Maybe it's here from the context, but and you can write this as e to the minus I over 2 Ji delta inverse Ij J. So remember when this is because I went to the eigenvalue case, this delta is like a diagonal matrix. So delta inverse is simply the diagonal matrix with each element replaced by 1 over delta. Okay, and so if you do that correctly, I think there should be an index here to track all the different eigenvalues. If you do it correctly, you will get a delta inverse here. Okay, that will generalize to delta inverse. And at that point, you can say, okay, good, but you still did it for the case when it's just an eigenvalue. It doesn't have to be true in general. So then, either you can do it in full glory because, I mean, at the end of the day, this is just, you can complete the squares. You just have to do a lot of work. Or you could say, look, this is all, let's at least restrict to the case when it's possible to go to a basis where the eigenvalues exist. So there's no funny business of zero eigenvalues and so on. In fact, all of that shows up in path integrals when things have a zero eigenvalue, like a zero energy state, like a long mode and so on, and it becomes important there. But let's say none of that happens. So then, I can just, even if this is not a diagonal matrix, I can go to a different basis. I can work in a basis yi dij yj, where y and x are related by the matrix containing the eigenvectors. You know this from your linear algebra. And so it's possible to go to a basis where it will become diagonal. Okay? Alright? Yeah.
So, when you change basis, so for the path integral, you have to change the path integral measure, right?
Good question, yeah. So strictly speaking, you should worry about that. You should worry about that if x becomes a matrix times x, right? But the point is that Jacobian, whatever the Jacobian will be there, will probably not depend on J. And that's what you are tracking. We are anyway throwing the constants, right?
Isn't the Jacobian just one? It's an orthogonal transformation of your basis test.
Yes, it's the determinant of that matrix, right? Yeah. Even better. That's right. Okay, so this is what it's supposed to be. And so good. With this answer now we already know. I already told you what this means. This means a lot of integrations. No index. Okay. And I already told you what that answer is supposed to look like for the x case. So that x is actually supposed to be this phi at some x, right? Hopefully you can see the connection. That x is the integration variable there. The corresponding integration variable is phi at x, not x. Okay. But with that change, we can already see the answer here. So that was what I was calculating. So before that, one quick thing. So notice that this has a form x delta x, right? So you want to write it in the form, so delta could, I mean, the way it generalizes when you make x from discrete to continuous is that it becomes an operator instead of being a matrix, because when you say xi takes a continuous number of values, those operators become, the obvious innovation is a differential operator. But to put it in that form, we have to do a little thing here, which again should be brought to your attention. So this term right now looks like this. d mu phi, right? And there's a d4x integration there. Now, this operator acts on phi, but I want an overall phi outside to make it look like that form. I have phi, then a matrix acting on x times a matrix acting on x. So I want it to go in that form. You have all heard about integration by parts. So what you do is, so phi d mu of the whole thing minus phi d mu. Okay, so this gets two terms because it's the derivative acting on the whole thing. The first term is when this acts on the first phi, you get this. And the second term is what I already subtracted. Okay, and then you have heard this again and again, hopefully, but this is a total derivative because it's d mu of something, and that when integrate over d4x will give you a boundary term. So it will just involve phi d mu phi at boundary. Now usually, unless there are some special field theories, phi goes to 0 at very large and long distances, and so this does not contribute. It is important in some situations, but for this case, you can safely say it's not important. So the point is that this effectively simply becomes minus phi d squared phi. And now it is in that form. It is phi times an operator acting on phi, right? So we'll use this. So all I'm saying is now, it is all right to just replace it with that. Okay? And so my corresponding delta is the following operator. Right? Questions? Any questions so far?
So usually we use plane wave states for phis, which
Don't
in
go.
far past are there as plane wave states. They don't go to zero.
Yeah, that's true. So I guess first of all, it should not depend on what basis you choose, right? I mean, the plane wave basis is just one basis. It doesn't have to be plane wave. Right? I guess the reason why you want phi's to go to 0 at infinity is so phi's are supposed to represent a particle excitation, right? And this assumption usually means that you have created everything here and destroyed everything here, in a finite space-time. It's not happening at the boundary of the space-time. And it becomes important in things like topological field theories and so on. But for simple cases, I think it's all right to drop the phi at the boundary.
But don't we assume that all our interactions and all our sources are present in my laboratory setting?
Yeah, but that's not infinity.
Yeah, that's not infinity. So all my phi's at t equals to minus infinity are out there at infinity, which means that at infinity they are not zero. They are zero in my laboratory.
Phi's are 0 in your lab. Why is that?
At t equals to minus infinity because they are supposed to interact in your laboratory. And the sources are in your laboratory, so these don't affect at t equals to minus infinity, which is one boundary. So at your t equals to minus infinity, all phi's are at infinity. That means they are not zero at infinity. They are zero inside your laboratory.
Even if it does not vanish, still that is just a proportionality factor, which is constant. And then independent of J, so we can just renormalize out. We don't have to worry about that.
No.
But if you drop that, you still have to integrate over phi, right? That's not true. I mean, so even if so what he's saying is it's a d mu times the whole thing, but d mu acting with this will just become overall factor.
Right.
But even that has a phi there, right? At some space-time point.
That is true, but anyway, phi is right now C numbers,
Mm-hmm.
so we're free to commute everything, meaning we can just factor that out, and then we can just evaluate that integration, which gives me Z independent constant. And then we can just say the same thing, just like any other constant factors we considered so far.
Yeah, I think I don't know the best answer for that question, so let's that. It is true that, the usual way I understood this is you have some sources or some, J is the pseudonym for a source, right? Which I thought of it in an electromagnetic sense. Whenever you have some charges or things here, the effect of that, which is the field, is not there at infinity. Okay. Now it is true though that when you do scattering experiments, the things that you are pointing out. So I don't know how that jump is, but it's fair enough to point out. So now, back to this. So we already know the answer for this, right? E to the minus I over 2. Now what do I do with the j, the index I in j? What should happen to the index I in j? How do I generalize it to this case? I can still work in a discrete basis. I can still make the x discrete. But I want the answer for this thing. Where x is a continuous variable. So the way is that you should think of x, the continuous variable, as the index of the matrix. So let me write the integration and then you will see how it makes sense. Okay, so this is the sum over I, this is the sum over j. J of x is the j sub I, j of y is the j sub j. That delta inverse is the inverse of this operator. Now what is the meaning of this? So notice that what does that delta inverse mean? It means the following. Delta times delta inverse is equal to identity, right? This is what you know from matrices. The generalization here is that some differential operator times the inverse of that differential operator, which I am writing by 1 over that, should become, so this is written in an index way, is delta x minus y. Because I can write this as this delta ij, delta inverse j, k is delta ik. Okay, something like that. But you already know what this thing is supposed to be. You already know what 1 over d squared. You have seen this equation before. This partial squared plus m squared acting on something giving you a delta function. It is the Green's function. And in fact, this is not just about quantum field theories. This is the general story of Green's function. Green's functions are the inverse of the differential operator, for which they are the Green's function, okay, by exactly something like this. So this already is the Green's function. So we already know this answer. Green's function for 2-point or 2-point function for the free scalar case is known, right? So this means that the answer is equal to e to the minus I over 2 j, so 1 for x and y. And I think there is an I there, a minus I there, where d is the propagator. Now how is that? Because I think conventionally this Green's function is supposed to satisfy the I equation here. I think the equation is this. Now correct me on that if I'm wrong by a factor, but and this is an x minus y, but this, let's say, is about x. The differential operator, you would say, is it about x or is it about y? So let's say it's about x. And I think you are supposed, this is the answer. So because I have a minus sign here, I will have a minus I there. And this will give me e to the minus half j dj, where that is the shorthand for j of x, dx minus y, and j of y, right? So this is an answer. Remember this, z of j, right? So this is the answer for the free scalar real quantum field phi with no interactions. Okay? Any questions? Maybe I should write it now in full glory so that stare at it again. So here is the full answer. d phi e to the I d4x d phi squared times phi squared times a half. Okay. This is e to the, which is also equal to e to the other. Now we did all this very fast without the epsilon. Remember we said drop epsilon, drop perturbations. But we also said just before that epsilon is important. Epsilon is important to make sure that things converge and so on. So let's just track epsilons in this and see where they show up. Okay. So that's why I think it will be good to have that expression here. But here is a quick shortcut way to track the epsilons. So remember we argued in the case of quantum mechanics, I showed you, please wrote the expression from last time, that when you put epsilon, in the end you get an e to the minus epsilon times the energy, right? And I also wrote the corresponding case for the field theory case. You get a phi dot square plus grad phi square and so on. So the statement is that if I have e to the is plus j phi, right, generically, this, when in the presence of epsilon, gives me the following epsilon dependent factors. There's an integration, d4x, let's say, phi dot squared over 2 plus grad phi squared over 2 plus v of phi. Okay. So what is happening effectively is that you are getting this combination in total. Okay, there is a I dt squared in here. There is a minus epsilon dt squared coming from here. A factor of half is also there in the action, right? Similarly, it's minus I grad square minus epsilon grad square, right? This is what the combination is appearing. You can just collect. All I'm doing is I'm collecting terms. Right? This term is also here, and you can just not do it this way. You can write the full thing and then collect terms and complete the square, but this will also give you the same answer. Okay? So this effectively means, so this will effectively mean the following. If because it is this, I can get the same thing by looking at the final expression that I have and letting dt become this. dt 1 plus I epsilon. So dt squared and grad squared go grad square 1 minus I epsilon. Because if so, I dt square becomes I dt square minus epsilon dt square. That's what we want, right? So this is what we should change in the answer over here. Okay. Now let's say what does that do? So in the presence of this prescription, that this will be equal to that, but with the following thing, right? So you will get implies we get limit. So of course there is epsilon going to 0 limit all the time. E to the minus I over 2 integrations, 2 j's. They don't care about this epsilon anyway. Minus 1 plus I epsilon dt squared plus 1 plus I epsilon grad squared, should be minus here, minus 1 minus I epsilon m squared. So let's just check quickly. There was an overall minus d squared plus m squared. Remember this operator was minus d squared plus m squared. There was a minus dt squared. So I should have a minus dt square times that. Then there was a plus grad square, so it's a plus grad square times that, right? And then the corresponding thing for the mass. Is the formula for the mass, right? So it's minus m squared and yeah, mass has the same sign as grad. So now let's keep going. By the way, is this fine? Anybody has any questions, at least about this part? Now there's something, I think my notes say this should be plus. Now let's just see why is that right or wrong. So I have a minus that square. Yes, this. So if I have an I have an I. Yeah. So this is correct. Okay. Anyway, we'll see what happens. So let's leave this here. And so, because of this, my G, let's say this, so, why did I call it a D? So this in Fourier space, in the Fourier variable P, will look like this. Right? I've just replaced these three factors in front of these three terms. So now let's collect. So p2 square minus p squared is p squared. And then I will have plus I epsilon p0 squared plus p squared plus m squared. Right? So far so good? Questions so far? So that bracket is a positive number. Right? So I can just call the whole thing. And okay, I forgot the minus m squared, right? So you can reabsorb that into epsilon, and then you have recovered back the p squared minus m squared plus I epsilon plus p. Okay, so it all hangs together. Good. So after this, so now we want to calculate endpoint functions for this guy. Okay, now we want to calculate the endpoint functions for this free case. Right? How are we going to do that? So recall that this, which is equal to z of j, or also e to the I w of j, was also equal to the vacuum persistence amplitude from the true vacuum to true vacuum in the presence of the source. Since it's a free theory, the true vacuum is the vacuum. You don't have to distinguish between 0 and omega. Okay, there's no interaction, so nothing is happening. So I want to calculate the following. So I want to calculate endpoint functions for this case. And so I have, how do I calculate endpoint functions? Well, I have to do this. quantities and acting on Sundrum. And this is a free theory. This epsilon does not have to be 0. And this will be evaluated at j equal to 0. Right? Why is this true? Because remember this quantity was also equal to this this thing in the presence of j was equal to IW, right? And this had e to the ij phi, something like that, right? So every time I differentiate with respect to j, I multiply with the minus I, I'm effectively putting a phi down. Times the same thing, right? And in the end, I'm setting j equal to 0, so that exponential is gone. So that is the endpoint function there, right? Okay.
Why are endpoint functions useful? Like till now we always used to evaluate 2-point functions.
Well, effectively, I mean, so for this case, we will show that this is just reducible to 2-point functions because it's a free theory. We already know that. But, I mean, in general, in an interacting theory, endpoint functions are useful, right? Because you may be interested in a process which requires 3 legs or 5 legs, which is with an interaction which has, I don't know, 10 kinds of loops going on. So, in general, those processes will be given by an endpoint function, not necessarily 2-point function, right? For example, if I gave you this, something decaying into 2 in the presence of interactions, so this shaded region is a shorthand for this plus some loop plus so on, right? So they're all three. This, they all contribute to the 3-point function, right? So every interaction, every 2 to 2 scattering, 2 to 3 scattering, every decay is a higher point function. So that's why those endpoint functions are used. Yeah, this is how endpoint functions are written as, which contain this plus all interactions are written as a shaded region. All right. But we already know the answer for this guy. We already calculated that, right? This, which was equal to the omega omega, which is equal to this, which is equal to this. We already know the answer, right? So we just have to differentiate n times the exponential and then set j equal to 0. Right? Now here is what I'm going to say this and then maybe it will be clear, or maybe I'll try to make sure that it makes sense. The only way you will get a non-zero answer here is in the following. So this will be equal to sum over pairs, product of G xi minus xj. So what is happening? When you differentiate with respect to j first, you get the exponential times this factor here down, right? The next time the d over dj hits this, it has a choice. It can either hit the factor here, which has a j, or the exponential. If it keeps hitting the exponential, it will keep bringing down the factors of j in front. And eventually when you set j equal to 0, it will all go away. The only way it can survive is if the d over dj hits the j here. Okay? So the only way this will give you a non-zero answer is the first dj hits the exponential and the second hits the j coming here. Right? And this is true for all j's. The two of them can do that. And every pair can do that. And then every time it does that, it will bring out a g with that corresponding x and y. Is that clear? Okay? If it is confusing, you can always make it discrete. Remember, this is the trick you always do whenever you're not sure about this continuous variables. And then you can even make it simpler, just make it one variable. Okay, and then you can see, is this making sense? And hopefully it will. So the point is that for the free theory, just because of this special form that it has, the only way you can, the endpoint function will only be equal to this. And something else. This is only true when because you want to form pairs. If you have 3 j's, or if you you have a 3-point function or a 5-point function, once you differentiate, once you form the pairs, the odd guy will bring a j out, and then you have to set it to 0 and the whole thing will vanish. Okay, so, but this is very good because you know from your canonical quantization that an n-point function in free theory is simply a bunch of 2-point functions. So here is the Feynman diagram, the corresponding Feynman diagram for that. So for example, for a 4-point function, this is something you might have seen it in Peskin. So you have 4-point functions x1, x2, x3, x4. The 4-point functions for free theory will only have either the two particles go this way or this way or this way, but they don't talk to each other. Makes sense from intuition because it's a non-interacting theory, right? And this is what this whole path integral thing is studying. In a more slick way, but that's what it is. Now let's build on to that and let's put interactions there. Okay, we just didn't put any interactions. So now now you can leave this answer in here. So put interactions now. For example, the Lagrangian you can add the following term. Okay, 5-4 term in the potential. This is the first case of an interaction. You can have more kinds of interaction. You can even have a 5-cube interaction, a 5-5th interaction. But let's just, it doesn't change anything. So now when you have an interaction, then here you will have a term plus I lambda over 4 factorial 5 to the 4, right? You're supposed to consider the full action. So the full action is d4x over the full Lagrangian. So the interaction will go there. Lambda is our small parameter. We are doing a perturbative expansion in the small parameter lambda. Now, clearly, this was a Gaussian, so we could do all this song and dance and we had an answer. This changes that. Once you have a 5 to the 4th, you don't know. There is no closed form answer for, it's not a Gaussian anymore for that expression because it's a 5 to the 4th. Right? It's a quartic. There's no quadratic form anymore. But the way you do it, and this is of course the whole point of working in, if you could do the whole thing without making lambda small, that would correspond to having a closed form expression, then there would not be any problem, right? Then you just solve the whole theory because it will give you a compact answer and then it's just a matter of differentiating that. But you can do it. There is no known form of it. So the way you do it is, so this contributes the following, right? So this implies we add e to the I d4x L, right? So the way you're supposed to make sense of this is you have to expand. So you make this equal to sum over n equal to 0 to infinity. So this L, let's put the form. So you get I d4x lambda over 4 factorial y of x to the 4th n. Right, so this n over n factorial is simply the exponential expansion, and of course notice that if you have n equal to 2, then there will be a d4x and d4y, right? There's no reason to call them x anymore. So if you have to any order you go, you will have that many integrations there. Right? And now this starts to look very similar to the master formula that we had in the canonical case. Because if you add an interaction like that, L int, that is the same as adding something in the Hamiltonian, H int with a minus sign. And that's what we had. We had in the master formula we had an e to the minus I h int, remember? But that is the same as e to the I L int. So it'll all come out the same. So let me just add that. So L int is related to h int, and recall that the relation between h and L is h is pq dot minus L, where p and q are the canonical momentum, and the q is the coordinate and p is the corresponding momentum. Okay, and you can convince yourself that if the interaction term does not contain any derivatives, then the change in the Lagrangian simply becomes a change in the Hamiltonian. Okay, the first term does not matter. So if you change something in L, it changes by the negative amount because they have a minus sign with it. Okay, so let's say, what do I have to say here? Okay, so let's keep going. Yeah, so e to the I d4x L int is equal to e to the minus I d4x h int, and which has this sum minus I integral v int to the n over n factorial. So from h int to v int is the statement that there are no derivatives in the interaction, right? So 5/4 is like a potential. Okay. If you have a derivative in the interaction, then the p changes. The canonical momentum changes because of the new terms. Canonical momentum p is the derivative with respect to so it changes, and in the canonical case of quantizing, it is very treacherous. When you have a derivative interaction, it's not clear because your canonical momentum changes and so on. But from the path integral, it just comes very naturally. But we're anyway not doing that case. And so this tells me that this endpoint function, so this is phi of x1, let's say, to phi of xk. So what did I do? I want to calculate this. I want to calculate the endpoint function in the interacting theory. Remember, we did that for a free theory. Or a k-point function. It doesn't matter. So what do you do? Well, you differentiate with respect to j, k times. Right? That's what the definition is. And that's how we got these terms. Right? But remember, the interaction does not contain a j. And I have already written the exponential in terms of a whole power series. If that power series just comes along. Once you brought down the interaction down, once you brought down, let's say, phi to the 4th as a power series, what remains is just a Gaussian again. Right? And so you can do that. In other words, all I'm saying is, I had this, I knew how to do it. Then I added a lambda phi to the 4th here, and I did not know how to do it. So I brought it down. I wrote it as an expansion series. To do that, I had to say that lambda is small, otherwise it would not make sense. Okay? If lambda was huge, then that expansion does not make sense. Because I'm going to terminate it. I mean, exponentials have a series for every value, but I want to terminate it, right? So that will not be justified unless lambda is small. And once I do that, then I can do the Gaussian, and every factor in front of the Gaussian is just comes by differentiating, right? You probably know that. If you have a Gaussian form and you have a bunch of x's in front, you can keep differentiating and getting the form. So it's doable then. So So this, okay, so this comes from d over dj, partial over partial j. And this is coming from lambda expansion. Right? And if let's say lambda was 0, because each of this has actually a lambda hidden in it, right? So let's say if you work to leading order lambda is 0, then this term will, there's also, so this also goes from n equal to 0 to infinity, right? So the first term is just 1. So you will just get the free endpoint function. But then there will be a correction because of considering this. And now, if you recall, all of this is actually, the way we were calculating loops and so on. We were using the interactions and doing some internal lines, doing some wick rotations and so on, right? It's all now repackaged, redone in a path integral way. It's all doing that.